Hello, this is Dr. Johnson. I am one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on sampling distributions of sample proportions. So just as a matter of review, a sampling distribution occurs if I take all samples of the same size from the population, and for each of those samples, I calculate a sample proportion. Of course, the proportions will vary from one sample to another, and we'll end up with a sampling distribution of sample proportions. Let me just illustrate it with this candy machine right here. So let's say that 40% of the candies in here are orange. So the true proportion of candies in here that are orange is 0.4. Rho is equal to 0.4. The number of candies, let's take a sample of size 25. So N is equal to 25. And let's just take one sample for starters and see how this works. I'm going to draw my sample right there. It's working, you can see. So it drew one sample of size 25, and as luck would have it, 52% of the candies that it drew were orange. So on my distribution down here, it put one dot. That dot right there is at 52, at 0.52. That's the start of my sampling distribution. But I don't want just one. I want lots and lots of samples. So I'm going to increase it. I'm going to add 999 more so that I have a solid 1,000 samples. So here we go. There we have it right here. And what you can see is that I have now a sampling distribution of sample proportions. These are the outcomes. This is a graph of all my different p-hats from my 1,000 samples. And you can see there's a center right about here at this right here. That's the center. And I can do calculations with this. I want to say, well, what is the probability? What is the probability of getting a p-hat less than 0.3? Some of these are more than 0.3, some are less than 0.3. What is the probability of getting a p-hat less than 0.3? So I've shaded in red here all of the p-hats that were less than 0.3. And if you could see here, the proportion in this sample, there was 160. So 0.16 of all of the p-hats were less than 0.3. So we can do calculations using the outcome of our sampling distribution right here. And looking at the shape here, I hope you can see that this is approximately normal. It's approximately normal like there. So let me just go over here and start my slide presentation. There we go. So let's first start. I want to show this slide right here. This is the definition of p-hat. The sample proportion of successes is p-hat. And how did we get p-hat? We took the total count of successes in a sample, and that's x. I divided by my sample size, that's my lowercase n. So p-hat is equal to x, the number of successes, divided by the sample size n. So this formula right here is the link between, or the connection between a sample proportion, p-hat, and the number of successes in a sample. Now p-hat, we put a hat on top of our p to show that we're calculating this p-hat based on sample data. It's calculated from a sample, and so we put a hat on top of the p. This graph indicates what we're trying to get out of this analysis. So we have a population there on the left, and we take lots and lots of samples of size n, and for each sample we're going to get a p-hat, and all those p-hats are going to be different values, and we're going to have a distribution. In this lesson, we want to figure out, well, what is the spread? What is the standard deviation of that distribution of p-hats, and what is the center of that distribution of p-hats, and what is the shape? That's our goal for today's lesson. Now, I'm going to show you this slide right here. And in this slide, I use the binomial, the definition of mean from our binomial distribution and the definition of standard deviation from our binomial distribution. And from that, I derive the mean of p hat. So the mean of p hat is rho. And this confirms that p hat is an unbiased estimator of rho. And I'll also, from the standard deviation of the binomial variable x, I derive the standard deviation of p hat. And that's equal to the very bottom equation. It's equal to the standard deviation of the quantity rho times 1 minus rho over the sample size. Now you can pause here and you can work through this math and see that my math is correct, but I'm going to continue. I will note this. I'll note this on this next slide. So if sampling is random, the sampling proportion p hat has a mean of rho. So the condition that you need to show to know what the mean of p hat is, we have to make sure that our sampling is random. Then, if the 10% condition is met, the sampling proportion has a standard deviation equal to that equation at the very bottom. So notice here that the sample size n is in the denominator of the right-hand side of that equation. So we can ask you this question. To cut the sample standard deviation in half, by how much must you increase the sample size? So if I want to make the right-hand side equation equal to, cut it in half, what must I do to sample size n? Well, the answer is I have to quadruple the sample size n. So just think how that works. See how that works. If I quadruple the sample size n, that is effectively cutting the standard deviation of p hat in 2. Okay. The formula, this formula at the very bottom there for standard deviation of p hat, that assumes that the samples were taken independently without replacement. If we are sampling with replacement, then we have to check the 10% condition. If the 10% condition is satisfied, then the fact that we sampled without replacement has a negligible impact on our calculations. The next thing we need to do is we need to check we want to determine what the shape of the sampling distribution of p hats is. Well, the binomial distribution is approximately normal as long as the large counts condition is satisfied. What is the large counts condition? Large count condition is that n times rho must be greater than 10, and n times 1 minus rho must be greater than 10. Sometimes we say that the large count condition requires that the counts of success and the counts of failure each must be greater than or equal to 10. So we have 3 conditions to analyze a sampling distribution of sample proportions. We have to check 3 conditions. First, the data must come from a well-designed random sample or a randomized experiment. If it's not random, then we can't draw conclusions about the population, and we don't know whether our sampling distribution is centered on our parameter. We also have to check the 10% condition. When sampling without replacement, we have to check that the population is at least 10 times as large as the sample. In symbols, we say that my small n, that's the sample size, is less than my capital N, that's the population size, divided by 10. That's the 10% condition. And if that condition holds, then we can use our formula for standard deviation of the sample proportion. Finally, we have to check that the large counts condition holds. That is, we have to check whether n times rho is greater than 10 and n times 1 minus rho is also greater than 10. If that condition holds, then our sampling distribution of sample proportions is approximately normal. So when all of those conditions are met, the sampling proportion p hat varies according to an approximately normal distribution with a mean of rho and a standard deviation given by that formula right there. When we're analyzing sample proportions, or sampling distributions of proportions, we put a rho in the right-hand side of that equation on the bottom. And the small lowercase n refers to the sample size. Now, I'm going to introduce a new format for writing out your answers to FRQ questions. And this is the format that we want you to use from now on FRQ questions in this chapter as well as our later chapter. So the sooner you get used to using this format, the better. The format has an acronym. It is ICCI. I stands for identify. C stands for conditions. The second C stands for calculate. And the third, and the I stands for interpret. Identify, in the first part of your answer, we want you to define the parameter that you want to estimate. Secondly, you want to check the conditions. That is, you want to identify the correct method that you're using by name or formula and check whether the appropriate conditions have been met. Next, you do your calculations. If all the conditions are met, then you perform the calculations for the z-score and for your probability. Finally, you interpret the results in context. That is, you state your conclusion with justification, and of course, we want you to add context. So let me show you what that looks like in the context of a problem. Let's go to this problem over here. So let's say the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Now, we suppose that the true proportion is 80%. Suppose 80% of all middle school students in her school district are planning to attend that university. So rho is equal to 0.8. What is the probability that if we took a simple random sample of 125 students, we'll get a sample proportion of, at most, 75% or 0.75. Identify. Here's how you're going to approach the identify part. You're going to write it out. Write out your problem in the form of a statement. What do you want to find? We want to find the probability that a simple random sample of 125 will give us a sample proportion of at most 75% when the true proportion is 80%. In symbols, I can write it like this. We want to find the probability of getting a sample proportion less than or equal to 0.75 when the true proportion is 0.8. The second part, we have to check the conditions. I want you to start out with a sentence like this. If the conditions are met, we'll use the sampling distribution of p hat to calculate the probability. What the name of this procedure that we're using here is the sampling distribution of p hat. So I want you to mention the name of the procedure. And later down here, we're going to show you the formula. Okay. So the name of the procedure is the sampling distribution of p hat. And now we're going to check our conditions. Our three conditions were randomness, 10% condition, and large counts. So randomness. You can't just put a check mark next to the word randomness. You have to say something about it. And in here, we are told that we're taking simple random samples. So I can refer to that. The sample is random, or the sample is an SRS. 10% condition. Well, we're not told the size of the population. We're not told how many middle school students are in this district, but we are told that it is a large school district. So sometimes this happens where we just have to say, it is safe to assume Because this is a large school district, we can safely assume that there are more than 1,250 middle school students. Why did I pick that number? Well, I have 10 times my sample size. And as long as there are more than 1,250 middle school students, then it's true that my sample size of 125 is less than or equal to the population size divided by 10. So this is the way you want to answer the 10% condition. We can safely assume that there are more than 10 times the sample size middle school students. Next, we have to check the large count condition. So n times rho, that's 125 times 0.8, that's 100, that's greater than 10. Then I have to check n times 1 minus rho, that's 125 times 0.2, that's greater than 10. So all my conditions check. Now we're going to do the calculations. Well, before I can do my calculations, I have to figure out what is the center, spread, and shape of this distribution of p-hats. Because the sampling is random, the mean of all my p-hats is equal to rho. My distribution of p-hats is centered over rho, and that's equal to, rho is equal to 0.8. So the mean of p-hats is 0.8. The spread, because the 10% condition is satisfied, I can use this formula right here. And plugging my numbers into the formula, I get a standard deviation of my p-hat distribution of 0.0358. Now I have this note over here, do not round on intermediate results. Please, please do not round on these intermediate results. We're going to use this number in later calculation. And if you round at this early stage, that's going to throw off your later calculation. So don't round this number here. Last, we have to find the shape of my sampling distribution. Because the large count condition is satisfied, we consider the distribution of all of my p-hats to be approximately normal, and I summarize it right here. I summarize it right here in this equation, in this sentence. P-hat is distributed normally with a mean of 0.8 and a standard deviation of 0.0358. At this point, we have a Chapter 2 problem. Problem just like you did in Chapter 2. We want to find the probability of getting a p-hat less than or equal to 0.75. First thing we do is we're going to calculate the z-score for p-hat of 0.75. Here's my calculation. Z is equal to 0.75 minus the mean divided by my standard deviation. I get a z-score of minus 1.40. So I draw my normal distribution or my standard normal distribution. I want to label the mean. It's pretty convenient here to treat this as a standard normal distribution. Put a mean of 0 here, a standard deviation, put a minus 1 here, and I drew my border at minus 1.4. But you could also label this with population values if you'd like. I've drawn my diagram, labeled the mean and the border, shaded the area of interest. I'm going to shade this area to the left of that border. Now I go to my calculator. Turn on my calculator. I go to the normal CDF. I want to find an area under the normal distribution. So I use normal CDF. The lower bound is minus infinity. Since your calculator, you can't put in a minus infinity. You'll just put in a large, arbitrarily large, or arbitrarily small number like minus 1,000. The upper value is 0.75. My standard deviation is 0.0358. My mean is 0.058. Please write down your calculator notation and label all of your inputs. You press execute and you're going to get an answer like this. That is my probability. But you also have to write a complete probability expression like this. The probability of getting a p-hat less than or equal to 0.75 is equal to the probability of getting a random z less than or equal to minus 1.4, which is equal to my answer. This is what the answer my calculator gave me, probability my calculator gave me. So that I have to finish with an interpretation, that is my answer in context. About 8.13%, here's my 0.813, about 8.13% of all simple random samples of size 125 will give us a sample proportion of at most 0.75. That is the use of the ICCI method to answer that question. That's it for today. Thank you for paying attention. That's the end of the video. Thank you very much.